supervisor Mandari Kafar and Ersin and Emiliano from BART. So we're going to talk today about privacy in content-oriented networking. Sorry for repeating the same thing, but for those who are not convinced yet about the ICN, just a brief history about networking. So everything started with telephony, and at that time, everything was about wires. And then came internet, TCP/IP, will emulate wires and move to the host-based paradigm. But now, the users today are more interested in data and information, so we don't really anymore talk about host. And so there is a kind of shift in the communication paradigm, and this is due to two main causes. First of all, is because today internet is struggling with mobility, scalability, and security problems. And if we take a closer look to the current internet, we find that most traffic is already content-oriented. For example, CDN and peer-to-peer networks are content-oriented networking. And all of this is because users in application care more about what they are receiving and not from whom they are receiving the data. So we can say that host-based communication model is getting outdated somehow. So there is a few architectures, here is some notable ones that try to put this change in the paradigm, among which in Europe we have PSRP, and in US we have CCNX, NDN, and DANA. But if we take a closer look to all these proposals, we found that they are sharing the main component or building blocks, which are that content is named, so all objects are naming, and the name should facilitate the data dissemination and search. Second, the routing is based on names rather than content. The content delivery uses multipath routing, and we have this in-network caching, so all nodes are supposed to participate in caching and content networking. So here is an example. This is an operation in CCN. When a client needs a content, first of all, he asks using an interest, by sending an interest. The first router or the edge router will check whether he has this content in his cache. If not, the interest gets forwarded to the producer. And then in the way back to the client, we have two new operations, which are the caching, so each node caches the content, and we have also the signature verification, which provide us with authenticity and integrity checking by default. So as we can see, content-oriented networking comes with great potential for augmenting the bandwidth, reducing the congestion, providing security at the data layer. However, it remains an interesting question whether or not and to which extent these architecture address new privacy challenges. So our work is some kind of a systematic study of privacy in content-oriented networking, when we try to expose several privacy issues in this new architecture, and whenever possible, proposing some countermeasures. And we also highlight some open problems. In the second part, we also compare content-oriented networking to the internet in terms of privacy, and try to answer the question whether ICN are more privacy-friendly than today's internet. So the outline of the talk will be in two main parts, which are the privacy challenges in CON, and then the comparison with today's internet. So let's start with the first part. So we know that each privacy design brings some privacy challenges. And in content-oriented networking, we have four main design choices, which are caches. So now we have caches everywhere, which the threat here is that an adversary can infer who consumes what. We have content privacy because the content is not encrypted, so an adversary can spy on or censor the content. We have name privacy because usually the name is semantically correlated with the content, so an adversary can see what the consumer is receiving as data and, for example, profiling it. And finally, we have a signature privacy, since all content is signed, so an adversary can identify the communicating parties. So let's start with the first one, which is cache privacy. So using a timing attack, an adversary can infer if a victim has consumed some content. To do so, he starts by measuring the time estimating the time with the producer, which is RTTS, and then estimating the time with the content router, which is RTTC, and then finally he fetches the target content and compute the RTTT. So now he check whether RTTT and RTTC are close enough. If they are, he can say that the victim consumed the particular content. If not, but still RTT is smaller than RTTS, he can say that the content has recently been fetched from the producer. Otherwise, he can say that the content has not been consumed. So how we can protect the end user from this? A simple approach would be to delay all the requests. So whenever we get a content M, we measure the RTT M to this content, and all subsequent requests to M will be delayed with RTT. So the nice thing with this is that there is a formal proof that it achieves perfect privacy, which means that there is no adversary that can distinguish cached and non-cached data. And in this proof, there is no assumption about content correlation, no network topology. And finally, we still reduce the bandwidth because we are getting the data from the cache. However, the bad thing is that all the data will be delayed. So another approach would be to say, okay, now whenever we fetch content, we store the corresponding RTT, but also we generate a random number k, and we delay only the k first request to the content. So the benefit from this approach is that popular content are less likely to be delayed because we are only delaying the first k. And there is also a formal model to quantify the trade-off between security and privacy, and this trade-off is how you can choose this k. And finally, we still remove we still have this benefit of reducing the bandwidth. However, in this formal model, there is some assumption about content correlation, and we still increase the delay for non-popular content. So the third approach would be to say, let's link edge routers all together and create some distributed bigger cache. So the idea behind this is to increase the anonymity set of the user. So even though the adversary knows that the content has been consumed, is not able to pinpoint the user that consumed the content, because here the set of possible users is bigger, and we have as a bonus increase the hit ratio because the cache is bigger. However, we have to deal with the overhead related to the administrative collaboration, and we have potential delay because now we have distributed caches rather than a single one. So the second threat comes from the content, as it's not encrypted. So basically, as the content is not encrypted, we don't need there is no need for a powerful adversary to spy on the content. So we can just, for example, modify the content router so that he can spy on the content and censor some of it, for example. So here the problems come from the fact that there is a lack of confidentiality. However, we cannot simply apply like cryptography, for example, SSL, because we will lose caching. So one approach would be to use broadcast encryption. In the broadcast encryption scenario, the producer sends an encrypted message to a set of users, and only the set is able to decrypt the message. So the good point here is that the content is only encrypted once by the producer, and we still have the benefit of the caching, because the set of this user can get the content and decrypt it. And finally, as a bonus, we have fine-grained user control, as the producer can at any time revoke any key from any users. However, the drawback is that the producer has to generate a lot of keys, n, which is proportional to the number of users, and the producer public key and ciphertext is proportional to the square root of n, which is big. So another approach would be to use proxy encryption. In this scenario, the producer here will generate a pair of public and private key for each session, and he will encrypt the message using the session private key. And then the message gets disseminated in the network. Whenever the client gets the content, he will send his public key, and the producer can then create what we call transformation key. And this transformation key is sent back to the user. Now the user can decrypt the message and using the transformation key plus his private key. So the good point here is that the content is available for any users. Unlike the first approach where we have only a set of users, here any user can decrypt the content. We have also the content is encrypted once because the producer encrypts the content only once. Caching is preserved and we have fine-grained user control as for the first approach. However, since we are using asymmetric encryption, it's not that efficient. So this is the drawback of this approach. So the third threat is about names. We know that names in content-centric networking can be correlated with the content itself. So an adversary can just spy on the names and create some profile for the user. And unfortunately, unlike HTTPS, content names cannot be fully encrypted because they are used for routing. So we cannot just encrypt the content. So our solution is based on Blum filters. So we have two Blum filters, one Blum filter for routing tables, and another counting Blum filter for each forwarding interface. So the idea here is not to encrypt the content, but rather obfuscating it. So we are obfuscating the content name, and we introduce a very small architectural changes to the architecture. And as a bonus, we reduce both the size of both routing and forwarding tables. However, as I said, it's just obfuscation, so we don't have any guarantee about the privacy of this schema. And we have also to deal with false positive and periodic resetting of the Blum filter. So let's move to the final thread, which is about signature. So content is signed, and an adversary, for example, a government can use the signature to make censorship. For example, a government can decide to censor all content that comes from Google or Microsoft. So how can we resolve this problem? One approach would be to use group signature. This is group signature for Google. So the real group signature is as follows. We have users from a certain company and a particular user who is called group manager. And these users give the private key to the group manager who will generate the public key. So now, using the public key and the private key of any user can sign the content. And when verifying the content, you can only say that it comes from this company, but we cannot say from which user signed this particular document. So the good point is that signature is still verifiable. We can still say that it was signed by this company, but we don't know who exactly signed the content. And it's efficient in the sense that the signature size is not related to the group size. However, we need the presence of a group manager, and the censorship is still possible based on, for example, the company itself. So another approach that tries to get rid of this group manager is called ring signature. And this approach, the user can use the public key of any other entities and sign the document. And now, when verifying the document, we can only tell that it was signed by one of these entities. That we cannot say who signed the content. So the good point here is that we have the signer anonymity, and we can still say that the content is trustful as long as all the signer is trustworthy. And there is no signer interaction and no group manager. However, there is some communication overhead which is linear to the size of the ring. So if the ring is too large, the overhead will be too large. And the censorship is still possible because we can always still saying that if the document is signed by this particular user, you can just drop it. So now I'm moving to the second part of my talk, which is about comparing content-oriented networking to current internet and in terms of privacy. And we'll start by anonymity. So in today's internet, the easiest way to achieve some kind of weak anonymity is to use a trusted third-party proxy. So it's just a proxy. And in Cohen, it's natively provided by the architecture because the neighboring routers is acting as a proxy. And so we don't have the source and destination address. So this weak anonymity is provided by default by the content-oriented networking. However, there is two drawbacks with this approach. First, both the proxy and the neighboring router represent a single point of failure. But most importantly, a local adversary would monitor all the traffic. So one solution in today's internet is to use mixed network. For example, Tor here, with the 3 hops, he can provide a very strong anonymity guarantee, and it's low latency. we have the equivalent for Tor in for CCNX, which is called Andena, and for the same guarantee, Andena needs only 3 hops to the destination. It's low latency. However, there is Andena disabled partially the caching because in the tunneling process, since the content is encrypted, you cannot use cache. So what about censorship? So we can, in current internet, you can do DNS tampering. It's effective in some content-oriented networking. We can do URL blacklisting, content blacklisting in content-oriented networking. However, these 2 approaches are easily circumvented in internet, and now most censorship relies on DPI, which is deep packet inspection, where we look inside the packet and decide, based on the content itself, whether we have to censor it or not. DPI usually implies that we have a strong adversary that have a specialized hardware to carry on DPI. However, we think that it's slightly easier in Koan because names and content are not encrypted, so we don't need a specialized hardware for that. However, I would like to stress that we know that it's easy done for a singular router. However, we don't know what's going to be the impact for the whole network, because now we can get the data from anywhere. So even if you suppress the data from a singular router, what happens if it's in another router that is not under your control? So the third privacy problem in today's internet is tracking. We know that using cookie, you can track users. So it's widespread, it's efficient, and it's tailored to business. What I mean about tailored to business model is that today personalization, for example, is based on cookies. Advertisement is based on cookies. So, however, porting cookies to Koan is more challenging as we don't have the same origin policy, because you can get the data from anywhere, so you don't know whether you have to send the cookie or not. We only can track dynamic content because the producer only sees the dynamic content. And finally, the question is how we can migrate the actual model that is heavily based on cookies to content-oriented networking. How we can do, for example, personalization and content-oriented networking. Is it feasible and how? The second way of tracking people is using status tracking. To the internet, for example, you can use the user ID and some host fingerprinting to do tracking. We think that it's more difficult in Koan because we don't have addresses, and since you are getting the content from any cache, the attacker sees only a proportion of all the traffic. However, the question is how, since we don't have addresses, how to handle security incidents, for example, how to block botnets, since we don't have the source and destination address. So the conclusion for tracking is it's true that content is more resilient, Koan is more resilient to tracking. However, it poses new challenges, basically business and security challenges. And finally, we check the data authenticity and confidentiality. We know in internet it's based on SSL. It's one size fits all. It's well studied and highly optimized. However, in content-oriented networking, it's an end-to-end model when different consumers can have different models. So you can implement a widely accepted like PKI, trust management model, or any other model. So the take-home message from this talk is that content-oriented networking are more resilient to traffic, and they provide some kind of deep anonymity as a native feature. However, they are possibly more vulnerable to censorship, and they pose some privacy challenges related to caching